Good morning, folks. This is the activity of week 7, June 28, in the morning session. It's a mechanism problem and taken from an old midterm. So read the instructions carefully, please, and you should be okay. You know everything that's needed uh, to be able to create this mechanism. Things look like. Now the problem is this geometry. So we have, it's made of essentially 4 parts. So there is a base here, there is a let's say this is called follower, there's this one that is called the driver or the disk, and then there is a coupler. Essentially this is the same geometry that I did in the class for you. It is the same one actually. uh, it's called the 4-bar linkage. Now you are asked first to animate this thing so that this disk turns, and the important dimensions are given so that this 4-bar linkage satisfies the Grashof condition. In other words, this disk will actually turn continuously, and when that happens, then of course this follower, you will see that it actually rocks back and forth. Okay. Now, the only dimensions that are important here that affects the kinematic behavior of this structure are given there. For example, I'm not telling you what these thicknesses are and things like that. But the only thing that's important is these, basically the support, the distance between the two support, etc. So my 4-bar linkage really has 4 dimensions. Uh, this length is 10, this is 10, this length is 2, this linkage is length 2, and this length is this link is 1.5 inches. Okay. Now once I basically make a cartoon here, create a mechanism, then I'm going to come back and put some physics into it. For example, I'm going to say that this disk turns at, I think I'm saying here, 240 RPM, which is 4 cycles per second, which means 4 times 360, whatever it is. Okay, uh, that many degrees in 1 second. All right, good. Let's not worry about that right now. Let me go make these pieces. So let's go here, insert. First of all, here's the product. Immediately I save it. So file, save management, save as on my desktop, a new folder, and I'll call this thing July 7 afternoon lab, right? And we say fine, put it in there. And let's do the base first. So insert a new part in there, and I'm going to call this thing the base. Right click properties. This is going to be instance name, base, and base. This is part name. All right, let's go make it. So we go here, double click on that. On a convenient plane, on that vertical plane, I will draw a rectangle and 2 circles which are 10 inches apart. So here is the rectangle. Okay, 2 circles, one over here. Just so that my job is easier, what I'm going to do is I'm going to actually give some dimension to this hole. Okay, so let me make this dimension 0.25. 0.25. Okay, and this one also 0.25. 0.25. Okay, and these are 10 inches apart. So from here to there, it will be 10 inches. Okay, good. So you know what? Let me do the following. Let me move this thing. Yeah, that's good. Okay, exit. And I'm going to make all these thicknesses 0.25 also. 0.25. Pad thickness is 0.25. You go all the way to the top. Let's do the disk. How about doing the disk? The disk looks just like that. Okay, so let me go ahead, insert, insert a new part in there. Say no. We're going to call this thing the disk, or the crank if you want. Think about it as a crank. So this is going to be disk, and down here is the disk, and let's make it. Double click on a convenient plane. On that plane, I will sketch. Let me make these things make my job easier. So why don't I project that circle? Okay, so there we are. And then I'm going to make a concentric circle here, like that. Okay, and yep, another little hole here. That's where the coupler is going to go, except that the only important thing is that the distance, well, actually, let me give this dimension 0.25 also, 0.25. Good. But one thing I know is that the distance from this point to that point, it should be 1.5, 1.5. Okay. Now, if it looks like that, no problem. We can make this thing bigger. So there we are. Exit. Okay. So I want to make it look like that. So I want a shaft here, no problem. So I'm going to do the multipath. You do it any way you want. It really doesn't matter. As long as you work it, that's great. So this is the whole. I'll leave it as 0. Okay. This one is the big circle, and I want that thing to be 0.25. 0.25. Actually, yeah, 0.25. That's fine. And then this one is that little thing in the middle that's going to turn into a shaft. So why don't I make this thing 1? Okay, so it looks like that. Of course, you want to turn this thing around and put it in that hole. I understand that, no problem. What is important is the distance between these two holes is 10 inches, and the distance between this hole and that shaft is 1.5 to take care of the kinematics of the problem correctly. Then I'm going to do the follower. So all the way to the top, why not click on the floppy so it saves that disk also. So insert a new part, and I'm going to call this thing follower. Right click properties, follower, and follower here. Follower. Yep. Let's make it. Double click on a convenient plane. On that plane, I will sketch. Now let me try to make it look like that, which is very straightforward. So I'm going to make, first of all, I project that circle. There we are. And then I'm going to make a rectangle here. Why don't I make this thing a centered rectangle? Like this. I may have to change the size of this because I need a hole here which is 2 inches away. So let me put the hole there, 0.25, right? 0.25. So I'm making all these holes to be 0.25 to make my job easier. And then the distance between the center of this hole to the center of this to be 2. Okay, that looks good. Very good. If you want to make these things bigger or smaller, that's entirely up to you, but it really doesn't matter. Look, the only thing that's important here is that distance from the center to the center of rotation should be 2 inches. Okay, exit. Once again, I'm going to do a multipath so to make my job easier. This is going to be the big thing, the big square here, so I'll make it 0.25, padded by 0.25. This is going to be the hole here. I'll leave it as a hole. And this one is going to be the shaft. So I think I made it one. I'll make the same thing here. There we are. Okay, of course, I'm going to turn this thing around and stick it in that hole. So the last thing to do is the coupler. So the only thing important about the coupler is that the distance from the two things should be 10 inches. Now, if I want to make it look like that, fine, no problem. Let's go ahead and do that. So all the way to the top, insert a new part. No, let's change this thing, call it coupler, properties, coupler, coupler, and coupler. Let's go make it. So let's see now. For example, yeah, sure, on that face. Yeah, on that face, I will sketch. Let's see. Why don't I be adventurous here? Let me use this elongated hole. So something like this. Okay, this distance should be 10 inches. 10 inches. Okay, good. And two little circles here, one over there, and another one over there. To be consistent with what I've done, make these radius 0.25. 0.25 and 0.25. Okay, and exit. I'm going to do a multi-pad. As I said, you do it any way you want. Make sure you can create geometry that looks like that. This is for the whole thing, so I'm going to make it 0.25, the big perimeter. Now these are both pins, so let me make it 0.5 and 0.5. 0.5 like that, and this one also 0.5. If you make it 0, if you leave it at 0, it's going to become a hole basically. There we are. Okay, so these things are going to go stick into that into these holes. Okay, good. Notice that they are pins. Okay, so all the way to the top, save everything. And let's go and do the assembly. So let me first move these things away from each other so that I can see what's going on. I'm going to translate this in X, translate this thing in X. Okay, the base stays stationary. You clamp it. Okay, good. Now let's put this pin inside of that hole. So coincidence between this axis and, if you have a hard time picking it, zoom in on that axis. Now, obviously, they are already coincident. There's nothing to update. That's fine. But also this plane and that plane. If necessary, we're going to flip. In fact, we do have to flip here so that it turns the other way around. There we are. You can see that. Otherwise, the pin would have been on this side. That's fine. So this is going to become a revolute joint later on. Coincidence, we do exactly the same thing on this side. Between this hole, what is that? This hole and that hole. What I meant, this shaft and that hole. Coincidence between that face and this face, the arrows should point to each other so that when we update, it positions the correct way. Good, good. This is going to become another revolute joint. Now I'm going to put this pin inside of that hole. Coincidence between this pin and that hole, and coincidence between this plane and that plane, and they should face each other. If not, just flip the arrows. Okay. Now this other one, let me move this thing a little bit so that rotate this thing about the, okay. You see, I don't have to make between this and this revolute. The cylindrical will do the job because these two planes will never get off each other. So these two planes will never get off each other. So I really need only one coincidence here. Coincidence with this axis and that axis. And they'll take care of it. It becomes a revolute joint, by the way. Now we can always check, okay? So let me go here, check this box, rotate about, how about rotating about this axis? Let's try it. This should go the way it's supposed to. Oh, here. You see this? That's a 4-bar linkage. This guy rocks. This guy goes 360 degrees continuously. Cancel that. Now, one other thing, because later on I want to plot a few things, and that point that I'm interested is actually at the center of this. I have to go to this coupler and create a point there. Okay, so let me do that. Let me go to that coupler. I have to do it in that coupler. And we do a point, create a point. No, this is selection filter. I don't want it. This is the point. Between uh, well, let me do it like this. First of all, you know what? The easiest way is this. Cancel that. Cancel that. Let me get these points first of all. Point, center of a circle. This circle. Here's one point. And we can do another one on this side, okay? Or we can do a point away from this in, you know, by 5 inches. It's easier if I did it same thing on this side, no problem. And then I'm going to do a point between these two. How about that? Between this point. Okay, I don't think I actually did this. This point. Did I create it? Let's check it. No, I just did one. Okay, so let's try it again. Center of this circle. And then say, okay, I think I canceled it the last time. And then a point between this point and that point. Did I do this? Well, where is this? Let me check for a second. It's this point. Oh, no, it should have been between, not zero, between, middle point. Okay, now that's better. Right there, right there. Good. So let's go all the way to the top, all the way to the top. Save. Cancel. No. Oh, I accidentally print. Oh, gee. Okay, I accidentally did something that I had to do a Control Alt Delete and get rid of that window. So what is it that I was doing? Save, right? This is the one that I wanted to do. I accidentally clicked on this printer and the driver was not available. Okay, good. Now comes the creating of the mechanism. So you're going to go to Start, Digital Mockup, DMU Kinematics, get the magic wand out, new mechanism, mechanism number 1, auto create, and let's cheat. There should be 3 revolute joints and 1 cylindrical. So let's check it out. Here is the applications, mechanism number 1, joints, 3 revolute and 1 cylindrical. Very good. Now the degree of freedom is 1 because if I make this thing angle driven, this is the disc or the crank that's going to turn continuously. Now, which one is this? That is the disc and the base. I'm going to make this thing angle driven between 0 and 360. Mechanism can be simulated. Can we do it with a command? Yes, we should. Right there. So you can see that it is doing what it's supposed to. Good. I always reset, close. Now let's create a simulation. Because to plot the trace of this, I think we were asked to plot the trace of it. Generate the trace of that point. Good, good. So you have to, first you have to create a simulation. Mechanism number one, you're familiar with this, drag it all the way to the end, insert, rewind, change to anything but one, and then you can play it continuously. Let's try it. There we are. This is basically just a cartoon. Well, I need to create this simulation because in order to create the trace, first I need a simulation and then I have to compile it. So you go to, again, the place that you actually use the simulation icon right next to it, compile, generate a replay, don't use one, anything but one, and play it, let it go through. Good. So you can see that a replay has been created and you can come here and look at it anytime you want. Okay, if you want to play it continuously, there we are. Rewind. Okay, now you're going to create a trace. Now that you have created a replay, you can go and do the trace. The trace is right here, the same place that you did simulation and you did the compile. Right there, it says trace. You click on it. What is the element to trace? It's that point. It's that point. 26 points. That's 26. When it creates a trace, you put 26 dots here. And it's going to create as a new part. This is why you have to save it and then bring it in as a part. Okay. If you don't save it and you submit your work, I will not know that. This is the path that it's going to take. So we go File, say Management. There is a trace that you created. Save as in that same folder, July 7 afternoon, trace 1. You save it. And remember, when you submit your work, if this was a midterm problem or final problem in this case, for exam problem, you just have to make sure that the trace is there. Now I'm going to close this. I don't need it, but I can say insert existing component, of course, in there, right? And it says which one? Well, I go to July 7 afternoon. This was the trace, and I say okay, and you will see the trace pop up on the screen right there. Now, if we simulate this, if you replay it, that point is right here. Okay, is right there. Look at it. It's going to traverse that path. Let's see it. Right here. So continuously. That point, the middle point, is going to go on this path. Good. Now we're going to put some physics into the problem. In other words, I'm told that the speed of that is 240 RPM. That means uh, uh, divided by second is going to be divided by 60 seconds. It's going to be 4 rounds per second, and 4 times 360 is going to be 1,440 degrees per second. So we're going to go to the f of x, click on the mechanism. The only thing that's important is this angle. The formula, that angle is equal to 1,440. That is 360 times 4. Yeah. DEG underscore either 1S or S, it doesn't matter. And if there's an issue, you go fix it. That's what times time. So the physics is in here now. Now, in order to plot stuff, you're going to have to create a sensor right here. It's called speed and accelerations. It's called speed and acceleration icon, but it is a sensor really. You click on it. It says, where is that reference product? Reference product is that base. That's where it's stationary. And point is that point that you created. Now, if you're having hard time seeing it on the screen, no problem. You can do it from the tree, or you can actually hide that trace. Where is that trace? Hide it, and you can see it on the screen, right there. Okay. So notice that it has been created. It has been created. So now you're going to go simulation. Well, let's before I do that, let's make sure we plot exactly what you were asked for. For the point x, plot the magnitude of the acceleration. Magnitude of the acceleration means no, don't look for the one that says x linear acceleration or y linear acceleration or z linear acceleration. Look for the one that says linear acceleration. That is the magnitude of linear acceleration. And this is one. And after that, plot the magnitude of the velocity against the magnitude of the acceleration. Okay. So here's what I'm going to do. First, let's do this part 5. We go to simulation with laws, right there. Activate sensor. Let's ask for the stuff that we wanted. And the first one was magnitude of the acceleration. This is speed. Further down, linear. This is angular, sorry. Linear acceleration, right there. Look at the unit, inch per second square. Per second square. If you can't read it, just make this thing bigger. Move these apart. The thing that I asked for was inch per squared second. Ask for this. Okay? Later on, I'm going to ask for also the speed. The problem is that if I tell you right now, also give me linear speed, because I need both of them, linear acceleration and linear speed. But if I do that, when you generate that plot, both of them are going to be on it, and I don't want it. So move this thing out. Over how many seconds? This is very important. Over how many seconds? This is very important. Do it only over a 2 second period. Okay, so make sure you change this thing to 2 seconds, not 10 seconds. Okay, play it. It's going to be eight rounds, right? 8 rounds of this going around, and then graph it right there. This, and zoom out, zoom out. This is the plot of the linear acceleration, magnitude of the acceleration as a function of time in 2 seconds. If you counted, there's 8 of these. Now, remember, you have to do a print screen, create a full a Word document, for example, paste in it, home paste, file, save as, that folder, which was called July 7 afternoon, right? July 7 afternoon. Where is it? Right there, July 7 afternoon. And I'm going to call this thing plot of linear acceleration versus time. Only give me this plot right now. And you can close. We're done. Now I close that. Rewind this. Rewind this. Make sure you clear the history tab, clear it. And now go and ask on top of linear acceleration that you already asked for, right there. You see that? Oops, linear acceleration. Ask for linear speed. Linear speed. Linear speed, which means magnitude of the linear speed versus linear acceleration, magnitude of the linear acceleration. Okay. So what you need to do is you have to run this, go to options, customize plot, add. Now what do I want? I want linear speed versus linear acceleration. It's this, right? Here, linear acceleration. Linear speed versus linear acceleration. You say okay, and close it and graph it. There we are. Zoom out, and then you do a print screen, create a Word document, paste it, and save it. File, save as, browse. In that folder, what is that? June, July, again, July 7. Right there. And I call this thing plot of linear acceleration versus linear speed. Say OK. And we put the physics into it. We captured the graphs that we wanted. We close this thing. I'm done here. And close this, rewind, close, save everything. We have managed to do this problem. So if we check our work right there, you have the product. You have the four pieces, the base, coupler, disc, and follower. You have the trace in it, and you also have the two generator plot that you're going to get marked on. Please give us only the plots that he asked for. Now, I do not mind if you put both of these in the same Word document, but make sure you say which one is which. Okay? Good luck.